Now, the law of conservation of mass is really important. It ties a whole lot of pretty critically important stuff together for us. So, what do I think you should know here? Modelling chemical reactions in terms of rearrangement of atoms. Yeah, that's that too. Energy, the role of energy in chemical reactions. So energy is obviously needed to bind things up. Well, no, we'll talk about that later. And this idea of the conservation of mass. Really critically important idea. So this dude's pretty famous. This is Antoine Lavoisier. He has one of those really rare things named for him, the law of constant mass. We don't have too many laws in science. It basically says matter is neither created nor destroyed, rather it is simply transferred or transformed. We'll also talk about that in this form of energy. So energy is not created or destroyed either, it's simply transferred or transformed. And Lavoisier unfortunately lost his head to the guillotine. So he's working in the time of the French Revolution. And the reason he lost his head is probably the reason he worked out the law of constant mass. He, by day, was a tax collector. He worked for the rich and the wealthy and collected their taxes from the people who worked for them, who were universally hated people, as you can imagine. But by night he was a chemist, and a world famous one. He won lots of awards and made some huge discoveries, including this one. So it was a bit sad to see his head lopped off, I suppose. But his accountancy, his bookkeeping, was what allowed him to see how this works. Actually, I'm going ahead of myself. I'll talk to you about that when I talk about balancing equations. So, we talk about endothermic and exothermic reactions. I know, more big words. If you break the bond in something, it normally requires energy to be put in to cause it to happen. So then that is an endothermic, a taking in of energy. When you make bonds, often you release energy because they're spare, and so they're exothermic. So they've released energy. So endo, inward, exo, out. And we see those two terms used a lot in different things. And the two steps take place in almost all reactions. Probably all reactions. I'm hedging my bets there. The difference is whether the amount of energy released when the new bonds form is greater or less than that required to break them. That's actually important when we start measuring energy, which you won't do unless you do VCE chemistry, probably. So, chemical energy can be explained sort of in the terms of being stored or in use in some way. So different chemicals have different amounts of energy due to the way that they're bound together. So this lovely diagram over here is showing us our coloured balls. So some oxygen, some carbon, nitrogen blue, I think, from memory. Phosphorus yellow. White ones are hydrogen, green ones, maybe that's, anyway. And these joiners, putting them together, are the bonds. You see here there's two bonds. So sometimes two are needed to join things together. That means there's probably more energy in that bond. So breaking that bond will release more energy than breaking that bond. Maybe. Can't really tell from the diagram. We need to know more information than that, but that's essentially the sort of idea here. We also talk about activation energy. So the classic example of activation energy is when you light a fire or a gas oven. You need a match, you need a spark. That energy of the spark is enough to get the fuel ignited. Constantly occurring in your car when you're a combustion engine. You're driving with a combustion engine. The fuel's pumped into the pistons, and the spark plug constantly sets a spark to activate the explosion to get the energy out of it. So some reactions need lots of activation energy, some don't need much at all, but they all need something to start them off. Hydrocarbons are one of those classic groups of chemicals we know a fair bit about because we use them as a fuel source. So natural gas is used in cooking and heating, less and less because it's getting expensive. We know it's also it's a fossil fuel, so it's limited resource and it's producing global warming problems. But your natural gas is essentially methane, but will contain some methane, propane, and butane. So these are all different amounts of carbons and hydrogens joined together. Now that's not a model of one. It's all I could find on the web to sort of illustrate a nice ring structure. But most of these have carbon rings in them. So methane is one carbon joined to 4 hydrogens. And then if we think, so it's called a hydrocarbon, carbon and hydrogen. Propane just has a bit more. It has 6 hydrogens and 2 carbons. And then, sorry, that's ethane. But propane has 3 carbons and 8 hydrogens. Butane, 4 carbons, 12 hydrogens, and there's a whole series of these hydrocarbons. Really useful for fuel. Lots of energy bound up in those molecules that we release by oxidizing, by burning them. Now we have different types of reactions. We have things called composition reactions. So substance A and B, our reactants, form our product AB. So examples always a bit better, I reckon. Nitrogen gas, N2, and G for gas, combined with hydrogen gas, which will give us 3H2. So H2 is a molecule of hydrogen, but we need 3 of them. We'll produce ammonia gas, and ammonia gas is NH3. But because we've got 2 N's there, we need another 2 there. I'll talk about that later. So 2NH, and again it's a gas. So reactant plus reactant equals product. And this is composing something new. Or we can go back the other way, and we call that a decomposition reaction. So there's our, in this case, our reactant, and it's falling apart. And we're getting the 2 things that was made it up are now separated out. You can have something called a single displacement reaction. In this case, I'm looking at silver nitrate aqueous, so it's a liquid, plus solid copper, produces copper nitrate and silver. So silver nitrate requires 2 silver atoms combined to a nitrate, which is nitrogen and oxygen joined together, and copper is just copper atoms. Copper nitrates 1 copper with 2 nitrates joined to it, and then we get silver falling out on its own. And a bit like we'll do that experiment at some point in class. Or we can do double displacement. So silver nitrate and sodium chloride produce silver chloride and sodium nitrate. So the silver and the sodium change place, and we get 2 new things. But essentially we still have chloride, we still have nitrates, we still have sodium, we still have silver. They're all still there. We just reorganize where they're sitting. So there's some chemical reaction information that might help some people with some questions.